Welcome back. It's my honor to introduce you to the speaker of the second session today. Uh, Samyak N is a driven aerospace engineer, first generation entrepreneur, and a technical leader. Currently holding the position of Chief Technology Officer at Akriti 3D Private Limited and Technical Director at Aakaar Precitech Private Limited. His unwavering passion for engineering innovation has been instrumental in establishing both companies as pioneers in 3D printing, 3D scanning, FEM, FEA, CFD, and precision manufacturing solutions. Samak's career began at the Gas Turbine Research Establishment, DRDO, where he served as a design engineer. Working alongside leading scientists, he contributed to critical defense projects, including the Kaveri engine and Ghatak engine. His expertise in metal additive manufacturing, gas turbine technologies, and advanced 3D scanning techniques has significantly advanced aerospace research and development. Driven by a vision to transform digital manufacturing, Samyak co-founded Akriti 3D, evolving it from a 3D printing startup into a full-fledged engineering solution provider. He further expanded his entrepreneurial journey by co-establishing Aakaar Precitech, a subsidiary focused on precision engineering and high-end manufacturing. Samak's innovative spirit is reflected in his intellectual property portfolio, which includes patents in agri-tech and aerospace. His recent breakthrough in aerospace technology, the Desert Boots innovation, addresses critical challenges in aviation safety, showcasing his commitment to solving real-world problems. Samek is dedicated to engineering excellence and fostering technological innovation. His journey is a testament to the power of technical expertise, visionary leadership, and an unyielding drive to push the boundaries of what's possible in the aerospace and manufacturing. Through his work, Samek continues to inspire and shape the future of engineering and entrepreneurship. We welcome you, sir. The dais is over to you. Thank you.
Okay, thank you, sir. I'll share my presentation now.
Yes, sir.
I hope my presentation is visible.
Yes, sir. Yes, sir. It is visible. Just click on that hide at the bottom.
Good evening, one and all. Thanks for giving the opportunity to be the part of discussion on functional grade metal matrix composite. So let's start. The thing is, I'll start with my company introduction. So we are an young aerospace engineers, design thinkers, passionate about bringing ideas to reality. We are a deep tech company where we solve industrial problems. Nothing but it may be in the mechanical stream, electrical stream, or electromechanical stream. And we are serving 180 plus clients. And some of our clients are Mercedes-Benz, SKF, Magellan Aerospace, and we do manufacture for Airbus and Boeing. And I just want to keep it brief and sweet. So what we address. So the thing is, if any product development or a new product development, there are certain common areas. One is conceptual design, and second thing is 2D to 3D, and third thing we will take that to the virtual environment where we do CFD and FEM, and then we move on to prototyping, and then we move on to batch production, QC, and DT. So our expertise is addressing entire area of this cycle. That is what Akriti and Aakaar do. This will be the outline of today's topic. Hence, there are people from different background. We'll start from briefing on composites and then and its application. Then I will move on to functional grade metal matrix and then possible case study of FM functional grade metal matrix. And also, we can start discussing about the different types of metal rapid type prototyping. And finally, we will touch upon the application of 3D printing in functional grade metal matrix. So The first question arises is why to study material science. To be able to select a material for given use base or consideration, cost and performance. And secondly, to understand the limitation of the material and change their properties. And thirdly, to be able to create the new material with desirable properties. Every industry is required different material and their requirement are different. So we required functional graded material for different industries. All the engineer disciplines need to know about materials. Even the most immaterial this thing like software and system engineering depends on the development of new material, which in turn alter the economics actually. So let's start with the basic. So the engineering materials are further classified into metals, polymers, ceramics, and composites. Now, for the past decades or so, the composite also plays an important role. Okay. So alloys. So in this slide, we'll discuss about the basic difference between alloys and composites. Like alloys is an homogeneous mixture, whereas composite is an heterogeneous mixture. Composites are engineered or naturally material occurring made from two or more constituent material. Now their material have significant different properties. When they are combined together, when they are combined together as a single part, they remain separate and maintain in their distinct identity at the microscopic level. However, the combination of these two materials, we get the new material which exhibits the finest property of the both constituent material. Such type of material known as composites. This difference from the alloys where multiple mixture of different elements when they mix evenly with each other in the microstructure. With a small example, we can address this. If salt is added to a water after some time, it will completely get diluted. This is how alloy works. Whereas you will look into the composite, if you add sand particle to the water, we can see the presence in the heterogeneous mixture in composite. And in the bottom of this presentation, we can see the microstructure of alloys and composite. We can come across lot of alloys such as bronze, and steel, etc. Now, the benefits of composites are like structural strength, lightweight, thermal resistance, and wear resistance, and flexible and durable. So now we move on to the topic. Main topic is called metal matrix composite. So metal matrix composite is a composite with at least two constraints. Okay, with at least two constraints. Part one being a metal necessary, and the other being the metal of different metal or any other material such as ceramic or organic component. So you can see the matrix metal of aluminum 365 and silicon carbonate reinforcement. So we know completely. We know the composite is made out of a matrix and a reinforcement. Reinforcement can be of several forms. So when we do mix this matrix and reinforcement, we get something called metal matrix component. So these are the possible matrices we have, like aluminum, magnesium, titanium, cobalt, nickel, and depending on our requirement, we can treat this matrix into alloys. So we can meet our requirement. So these are the reinforcing agent like aluminum, silicon carbide, zircon, titanium nitride, titanium carbide, cubic boron nitride. So the next thing is classification of metal matrix composites. So the metal matrix composite can be further classified into particulate reinforcement matrix composite. That means to say that to take a very small particle with the aspect ratio of less than 5, that is nothing but your L by D ratio. So we can try take a very small and disperse inside the matrix. So these composites are called as particulate reinforced matrix. And the next form is the short fiber or whisker reinforced matrix. The next one, with the slight higher aspect ratio, that whisker can be used as a short fiber can be used. So here the L by D ratio changes. So we can have a short fiber. It can be out of the fiber or it can be made out of fiber or glass fiber, or it can be made out of ceramic material. So it is dispensed inside the material matrix, so we can get a composite. So the last one will be going to be continuous fiber matrix, so or sheet reinforcement matrix. Composite where in which the continuous fiber or glass fiber or glass mat can be used or carbon owing will happen. In these three cases, metal will be taken to liquid state and then brought back to solid state. So you can do sheet laminate where in which the metal will be in solid state, and then the reinforcement and we sandwich it and we process it to get a composite. So these last two applications of continuous fiber finds at highest application. So when you talk about metal material composite properties, they are like high specific strength, specific stiffness is high, like temperature resistance, better fatigue resistance, better creep resistance, high wear resistance, corrosion resistance, and low weight. So when we make any product, the first thing or objective function, that is nothing but your mechanical property are very important, and physical property and electrical property. For example, the aerospace application, it always demands lightweight, high strength application. So it should have low density, high Young's modulus, high compression and tensile strength. Good processability, mechanical compatibility should be there, thermal stability should be there, and has to be economical. So these are the main properties which the MMC should contain. Like these are certain areas where MMC application is used. One is automobile area and aerospace and defense area, and there are plenty of areas we can address these MMC applications. So coming to the drawbacks of MMC, though it can overcome the disadvantage by alloy, there are certain drawbacks. That is delamination. This delamination is due to mainly of high coefficient of thermal expansion. As we discussed, our composite consists of two materials, that is reinforcement and metal matrix. Hence, there is a difference in coefficient of thermal expansion between reinforcement and matrix. They are bonded together. So, due to increase in temperature, one material tends to move less. Because of this, internal stress will be developed inside the component, so that the performance will be reduced, and also if there is any weak bond between them, the reinforcement matrix will be mismatched. So what is functional grade material matrix? So it is an advanced engineering material which is characterized by defined special grade properties. It is also called as innovative composite material. Uh, from the materials are completely different from the conventional the materials are completely different from the conventional composite material, and which are either homogeneous mixture or two or more materials, as in the case of laminated composite material. So you can see the structural grade of MMC over functional grade material here. So how did the functional grade material has been invented? The functional grade material is actually been developed by Japanese scientists in 1980s. The main reason of the development was when they faced the challenge of an hypersonic plane project, which require a thermal barrier with an outside temperature of 2000 Kelvin and the inside temperature of 1000 Kelvin across just a thin wall thickness of 10 mm. So they came up with a new material called functional grade material. FGMs are entirely different from the conventional alloy and composite, in which the mechanical, electrical, and magnetical properties are very smoothly and continuously in preferred direction. So they do not allow any stress concentration on any particular point. So the thing is, the importance of functional grade material. Functional grade material eliminates the sharp interface. You can see it here. Eliminates the sharp interface between the composite, which is where the failure initiated. It replaces the sharp interfaces with the gradient interfaces, which produce smooth transition from one material to the next material. For example, you can see the toughness of the material can be measured with the refractionness of the material of a ceramic without any compromising in toughness of the material side or the refractionness of the ceramic side. So classification of gems. So classification of this functional grade material can be like this. It can be metal to metal mated, ceramic with metal mated, metal with polymer mated, and alloy and other. It can be done according to the requirement. FGM may be compositionally or microstructurally graded, and depending upon the nature of the gradient, the functional grade materials may be grouped into following groups. One is fractional grade, and the second thing is shape gradient, and third thing is orientation gradient, and the fourth thing is size gradient. Uh, so the advantages of FGMs are, so the what is the FGMs we can see here, that is better adherence of the protective layer, and secondly the minimization of interfacial stresses between different material, that is nothing but evenly distributed. Okay, and the third is increasing in the local fraction toughness, that is strength of the material increase, and fourthly the relocation of maximum stress on load bearing component. So these are the various field of application of FGMs. Like you can use, it has been actively used in aerospace, aerospace industry, chemical plant, electronics, energy conversion, and optics, nuclear energy, and energy. So this is one of the example like case study for FGMs, where the re-entry of any airport, it encounters a high temperature in one side and the low temperature, comparatively low temperature on the other side. So the downside need a material with of high heat resistance and ductility. So FGM fabrication method. So the FGM fabrication method are classified into three parts. One is solid state process, and second one is liquid state process, and third one is deposition process. In solid state process, it is further divided into powder metallurgy, diffusion bonding, and additive manufacturing. Liquid state process is again divided into infiltration, centrifugal casting, gravity settling. And deposition process is like it further divided into three main parts, like vapor deposition, spray deposition, and laser deposition. So as the topic demands, that we will be talking about the additive manufacturing of FGMMs. So let's have a brief overview on 3D printing, or more comprehensively term, we may call it as additive manufacturing. Additive manufacturing of or 3D printing is nothing but adding materials layer by layer. That material can be in the form of solid, liquid resin, or powder. So we can join it later, layer by layer, to form a three-dimensional object. It was started with an approach of rapid prototyping with the rapid prototyping. With the evolution of different technologies, we are calling it as AM or 3D printing, where we can get up to a batch production. The AM process chain initiates with the development of CAD, and then we can move on to tessellation. That is nothing but piecewise approximation of developed CAD model, or we can just call it as mathematical modeling. Then we go to the next step, that is slicing. That is nothing but getting the layer by layer information of tessellated model. This is an important step. Hence, we know that the 3D printing is layer by layer manufacturing technique. And then we go for tool path generation, and it can be either nozzle movement in the case of nozzle based technology, or else maybe laser movement in the powder based technology. It is nothing but one dimensional tool path generation. Then the latest step will go to the corresponding prototyping, whether it may be a powder FDM, SLA, or powdered PET fusion, or then move on to the once that is done, then move on to the post processing, which is very crucial and mandatory in certain 3D printings technique. Then we move on to the final testing and the feedback loop actually. Uh, as we discussed in the previous slide, the first step in AM is generation of CAD model, and CAD model can be generated using different CAD softwares like CATIA, NX, SolidWorks, Creo, or maybe Geomagic, everything. There are other ways that makes 3D printing more interesting, like in which 3D scanning and reverse engineering is one of them. For example, let's consider we have a component which doesn't have any digital data existing. So, so with the help of 3D scanning, we just have to scan the component, and we'll be getting we'll getting a highly accurate 3D cloud point data, and that data can be reverse engineered and converted into CAD, and then it can be manufactured. Similarly, we can use this in biomedical, where the patient specific data of MRI or CT can be reconstructed and can be used for 3D printing for vital organs and prosthetics. Once the digital data is achieved using these different techniques, we convert this into STL, where we get a geometrical data like auxiliary supports and superstructure, which are very important in 3D printing. Then then we move on to the machine layer information like post process parameters, machine parameters. Now we have the machine data for further printing. So this will be the basic structure of 3D printing. So additive manufacturing is again classified into this substructure. If we are using a liquid base, then there is stereolithography. It is the first 3D printing technology developed. Then there is jetting system and bioprinting system. There are powder based techniques such as selective laser sintering, metal electro beam melting, different direct energy deposition. Then we also have solid based technique, where the material in the form of solid wire or in the form of sheet. Hence, the topic is related to the metal based AM. We'll stick on to the powder based technique and the fuse deposition method. Okay. In the powder-based AM, the most popular technique developed is selective laser metal sintering, or else called as selective laser sintering. If we talk about 3D printing process, there are two major aspects. One is achieving three-dimensional XYZ motion. That is our movement of our this thing. And the second most important thing is fusion mechanism. SLS is a layer by layer manufacturing process that allows the generation of complex 3D parts by consolidating successive layer of powder material on top of each other. Consolidating is obtained by processing the selected area using the thermal energy supplied by the focused laser beam. It was actually developed by University of Texas in 1989. This was originally developed to create plastic parts with lower melting point. Then the principle extended to ceramic part. So let us see the working principle of powder bed fusion. So in this diagram, we can see there are certain parts like powder filled cartridge, and the powder filled you can see the powder filled cartridge. The powder is filled in this cartridge. Then we can see a build space. Then we can see a laser focus area, and we can also see a ricotta, which is nothing but a powder feeding roller to build space for fusion. The powder in the cartridge, with the help of the roller, is spread uniformly on the top of the bed, and at the same time laser beam is focused. Selectively, it will move on X and Y direction. Once the layer is printed, the build envelope uh, go on to the negative Z direction. Next layer of unsintered powder is spread on the build environment. Then this repetitive process will cause sintering. When the laser is focused on the powder and gets sintered, the loose powder, whatever the loose powder remaining unsintered, act as a support structure. So this is about SLS, and in this powder bed fusion only, there is a next type of powder based AM is electron beam melting. Here, instead of laser, we use electron beam, that is called as electron beam melting. The purpose is to process the high melting temperature material like Ti-64 inconel. This laser power, whatever the laser power we discussed, power may not be enough for consolidating, so we use electron beam here. In this mechanism, there is a filament electron are released from the top of the this thing, and there will be an anode arrangement which will focus EVM. Then we use a magnetic lens to focus electron beam to the part surface. Then the rest of the mechanism is similar to SLM actually. Only EVM process requires inert atmosphere. There, that is nothing but your vacuum environment actually. So next thing is binder jet. The original name of binder jet was three-dimensional printing. Actually, it was invented at MIT, and it is also can be coined as the advancement of like conventional our 2D printing, which we use in daily life. Here we are using a binder jet to drop the binder on the surface of the bed in a selective surface where the powder is uniformly spreaded and the bed moves down and the process repeats. The working principle of the bindages is similar as whereas the recoater similar as to the SLS, whereas the recoater distribute the powder uniformly, and instead of laser, binder will come and deposit on the selective on the part and point where the binder is deposited. It will be joined actually. Advantages of this thing is fast printing, and process does not require any powerful source of energy like laser or EBM. This EBM and eliminate the defect formed during heating actually. And the limitation of this binder jetting is significant part shrinkage will be there. Lower intensity, hence it is based on binder. The part will be fragile with limited mechanical properties, and if not processed, the mechanical properties will be very low. So direct energy deposition method. In case of powder bed fusion technique, the biggest limitation in the powder has to be spread on the bed, and for that we need to have specific properties in powder, like flowability has to be there, packing, and so on. But sometimes there is a chance of not getting completely uniform spreading due to moisture and size of the powder, and it is also time consuming, and it delays the productivity also. Hence, to overcome the limitation and fabricate high melting metal, so a new technique is developed, that is direct energy deposition. In this picture we can see a powder entering from the powder nozzle. You can see it in the left and right hand side of the this thing, and there will be a shielding gas will enter from the corresponding nozzle also. You can see it over a inert gas environment on the outer this thing. And the laser will come from the center. As soon as the powder come in contact with the laser beam, it will be melted substantially, and it will be deposited on the part of, just like in FDM, and we deposit polymer. In DED, we are depositing molten material to the substrate surface. There are different surface of energy apart from laser beam, like tungsten inert gas, metal inert gas, and plasma arc. Advantages of DED is, like, the biggest advantage is, hence there are two nozzles. We can generate alloying of the material during the printing itself, and also fabricate functional grade metal matrix during the printing itself. So the material wastage is very low in the previous process. like like the unsintered powder, though it act as material, though it act as support material in material, some case it may not be used because of the thermal damage. The working envelope is like the advantages, main advantage is the working envelope is much bigger, because the in other PVF method, the previous method, it is like confined to the vacuum space and build base size actually. And it is effective for both fabrication and repairing. And the one more advantage is time and machining cost saving is there. Hence, there is no powder centering. The main next move on to the if you move on to the limitation of this direct energy deposition method. So there is a certain limitation. We also need like it has to have support structure. Hence, it is attached to the molten material. The support structure removal is very difficult in DED because it requires post machining. We need to have machining out. Suppose it is very time taking actually. Now we'll start discussing about the case study of an functional grade metal matrix using direct energy deposition. So this was the objective of this thing, to fabricate a functional grade based material composite like aluminum silicon carbonate using DED for aerospace application, functional on achieving high strength and wear resistance and thermal stability. So the material matrix was aluminum alloy was chosen, so it was good, weldability was there and melting point is very high, and the compatibility with the SiC reinforcement is very good. The reinforcement material is considered as silicon carbide material with the 10 to 20% by weight, selected for its high hardness, and thermal conductivity is very good and wear and resistance. So the equipment we have used is laser-based DED with the 2 kilowatt fiber laser. The process parameter are as below. Like laser power is around 800 to 1200 watt, and scan speed is around 5 to 10 millimeter per second, and powder feed rate is around 2 to 4 gram per minute. Actually, the layer thickness is around 200 micron to 500 micron, and the shielding gas was around is like argon or neon to prevent oxidation. The building strategy was multi-layer deposition with a zigzag pattern to ensure uniform distribution of SiC particle actually, to eliminate the thermal stresses occurred because of layer by layer deposition of molten metal actually. So these are the challenges we have encountered. One thing is SiC particle tends to segregate during the deposition, leading to inhomogeneous mixture actually. That we encountered with optimizing powder blending and control feed rating to ensure the consistent reinforcement distribution. And the second challenge was thermal stresses and cracking. Hence, we all know that this technology is layer by layer technology. Once once the molten metal is spread, and between the first layer and the second layer, the molten metal has to cool it down in a drastical way to eliminate these thermal stresses. So this we have encountered by preheating it into the 200 degrees Celsius and using a lower laser power to reduce thermal stress actually. And SiC decomposition actually, high laser energy can decompose SiC into silicon and carbon, degrading the composite material. So what we did was optimize the layer power and scan speed to minimize the excessive heat input actually. So results and characterization. So microstructures SEM analysis revealed that to inform distribution of SiC particle in aluminum matrix, no significant decomposition of SiC was observed actually, and indicating optimal process parameter. So mechanical properties like hardness was around 120 to 140 HV and compared to 60 to 80 HV per. So tensile strength was around 350 to 400 MPa, and 30 to 40% improvement over the base alloy we have found out actually. Wear resistance was around 50% reduction in wear rate and compared to the reinforced aluminum actually. So the thermal conductivity was 160 to 180 kilometer. the suitable for heat exchanger application. Actually, the coefficient of thermal expansion CT reduced by 20% due to SSC reinforcement. So the application, this is the main the fabricated aluminum metal magnetic composite is suitable for like application like corresponds component like blade, bracket, heat exchanger, and fuel nozzle, etc. In automotive parts, it can be used in piston, brake rotors, wear resistant tools and dies. And the conclusion, what we got from this case study is the case study demonstrates the successful fabrication of functional grade aluminum silicon carbide metal matrix composite during using DAD by optimizing the process parameter and addressing the challenges such as particle distributed and thermal stresses. The DAD process can produce MMC with enhanced mechanical and thermal properties. This approach opens new possibility for the lightweight, high performance component in the demanding industries. Actually, okay, thank you.
So thank you, sir. It was a very good presentation. Any questions from the participants? I just unmute all. Yeah. Any questions, participants? I think Dr. Mahadev Madhugule and Vishnupan sir raise the hands. We are unmuted, sir. You can speak.
Sir, it is Vishnupan Misale here.
Hi, sir.
Sir, I just want to know, you mentioned this cracking, and then we have to do the preheating for avoiding the cracking. Any method for after cracking, whether it can be repaired?
Sir, there are a few things. One is furnace we have to use actually, and
Yeah.
once that is done, once the thermal stresses are removed, then we have a certain method called a plasma arc, which has been developed. Using that, we usually do this cracking repairing thing actually.
Okay. So this the same method cannot be used, that 3D printing itself, to arrest the this thing, to repair the cracks.
Sir, as if it is a layer by layer this thing, no? So again, the exact position data at the achieving will be very tough. So that is one of the like there are certain research going on this area to time parametered correction area. So due to like interface between the logic of software and this thing, it has been not possible at now.
Okay. So, I was of the opinion that this particular technique, by making it as small as possible or the as portable as possible, whether we can make it is important. Then, if we make it, will be helpful in repairing the cracks or the defects in the materials, so
Correct,
that
sir.
lot of resources can be reutilized. See,
Correct, sir.
most of the in aerospace components, if there is any crack, they will simply reject it now.
Yeah, yeah, sir.
So there should be a mechanism by which we can repair. Maybe
Mm.
this 3D printing, using this small portable systems, so that we can go to a particular. For example, in an aircraft, if there is a crack developed and if it is noticed, at least we should be able to repair that in situ. So such mechanisms should be thought of.
Yes, sir, definitely, sir. And when we talk about DED, that is the most probably next thing which can address the repairing thing, actually, sir.
Okay, sir. Thank you.
Thank you, sir.
Any other questions by the participant? Any other questions by the participants? Mahadev sir, Dr. Mahadev. Dr. Mahadev sir, I think just in the chat box. Yeah. Unmute. Yeah. Okay. So, if there are no further questions, then we will end the session over here. And thank you, sir. Thank you, Samyak sir, for your valuable insights. Now we are going to share the feedback link. All the participants are requested to give their feedback, and time span is 5 minutes. So within that window, please give the feedback, all of you. Okay. I once again thank Samyak sir for spending his valuable time and giving us the detailed explanation about 3D printing of functionally graded metal matrix composites. Thank you, sir.
Thank you for the opportunity, sir. Thank you. Have a nice day.
Next, please. Yeah, please, all of you give the feedback.